Well, it's time to figure out some heat from a microwave. Find out what a microwave can do and convert its microwave energy into joules. And we have our calorimeter here, our nice little styrofoam cup with a little plastic liner in there, just so that I don't poke holes in that soft foamed polystyrene. Okay, first thing we've got to do is figure out our calorimeter's mass, and that's going to be pretty easy. I've got my balance here, and I'm going to go over on this side, zero my balance. There, we've got it zeroed, and record the empty mass of this calorimeter. And we've got it at 17.77 grams. I'll write that down right now, 17.77 grams. And that last milligram is pretty tenuous because I don't have a shield on it. And now I'm going to get some cold water to put in here. And I'm going to get about 70 or so grams, which will really be 70 about mLs of this pre-chilled water. So I'm going to estimate from the crude markings on this beaker, which are they're just estimates. There we go. We've got about 70, maybe a little bit more mLs of water. This is going to be chilled. It's been in the fridge for at least 20 minutes. And I'm going to get my thermometer, turn it on. Let's see, what does it say? 68 degrees. Well, that's got to be Fahrenheit. 68 degrees Celsius. We'd be cooking. We'd be well done. Right now it says 24, and I'm going to check out that temperature of the water. Oh yeah, I've got it chilled nicely. Now, let me get that temperature. It looks pretty stable at about 8.8 degrees Celsius. I'll write that down. That's our temperature 1, 8.8. We've only got two significant digits on that, but let's see, we're interested in the change in temperature more than the absolute temperature, or more than the degrees Celsius. And it's staying pretty stable there. So we've got some good insulation. I don't see it warming up too much. So, okay, I'll take that thermometer out. And now I'll go to the microwave and give it a zap of 40 seconds. Okay, now it's time to get our cold water that we've got in our calorimeter to trap all that heat that we're going to put in there for a while into the microwave. So here is our microwave. I'm going to put it on the turntable and set the timer for 0 seconds and get it started. The microwaves are being generated by that little magnetron device, and they're visibly bouncing around inside the container there. And as the microwaves move past these water molecules, the dipole of the water molecule will make them flip back and forth, and as such the water will end up gaining kinetic energy. The average kinetic energy of the water will increase, and we'll find out the energy of those photons that have been put in there, because we're going to take the final temperature, we know the initial, and we'll know the mass of the water, and we're going to figure out the joules that are now trapped in there. The microwaves, photons changed into joules of kinetic energy. These, nice warm calorimeter. So let me get that temperature as soon as I possibly can, so I don't lose any of those joules. We're going to take the temperature as fast as we possibly can, because I'm sure the temp's zoomed up quite a bit, and I'll give it a good stir. And right now, okay, we're up to, whoa, that's scalding, at 73 degrees, 73.8, 73.9. There we go. It was at about 73.9, and the temperature is dropping pretty quickly. It's already down to 72.5, 72.3, 72.1. We're losing about 1/10 of a degree Celsius in temperature per second as these joules of energy leak out, probably coming out of the top into convection into the air, and we're at 71.3 degrees already. They used to think of heat as a fluid, an invisible fluid, and that's not a bad way sometimes of looking at it. They call them calorics. So these calorics are escaping as we see them. It'd be tough and stuff too. So that initial temperature is pretty important. So in fact, sometimes people will time things and find out how quickly the temperature drops and then extrapolate back to zero to get the temperature at zero. But here we are down to 69 degrees already. That energy goes from hot to cold. That's one of the major rules of thermodynamics. It doesn't ever go the other way around. And if it does, time's going backwards, which is not a very good thing. So, okay, we've got our temperature too. Now we have to find out how much water was heated. We'll presume the styrofoam cup didn't absorb much heat. That's one of the possible errors in this experiment, but I've zeroed things out again, and let's see what we get for our final mass. Our final mass is 80.72 grams. Now it's it's dropping a little bit. It's not, in fact, it's down to 80.7. I wonder if the water is evaporating because it is hot enough. In fact, actually, probably what we're seeing right now is dropping to 80.66, 80.65. It's a complete drop. We're losing about 1/100 of a gram every 2 seconds or so. So that water must be escaping it, breaking those old bonds and probably cooling the water too. That'd be another factor. So, okay, here we are. We've got our data. We've got our mass of the calorimeter was empty, and of course when it had water in it, so we can find the mass of water. We can figure out the temperature change of the water, and we'll assume the specific heat of water is 4.18 joules over this temperature range. And that way we can figure out how many joules were absorbed by the water. And this microwave was a 1,000-watt microwave, which means 1,000 joules every second. So you can figure out how much the microwave output was in terms of its photon energy. And then we can see how much of that photon energy was actually used to heat the water and find its percent efficiency. So you've got all the data you need for this lab write-up. Okay, that's it.